Hello everyone. In previous two important sessions, we have discussed the application of electrical analogy to plane wall when slabs are in series and plane wall when slabs are in parallel. Now we are going to see when there is combination of both of these phenomena, then how do we deal with the problem? So for this particular section, we are going to see a plane wall which is made up of combined series and parallel slabs. So let us say this is the first slab, this is the second slab, and then this is third and fourth slab. Rather, I will say that this particular slab is again divided into two different materials. So this is material A. I will call this as material B. This is material C. This is material D, and finally this is material E. So in this case, what we observe, the cross-sectional area for entire material A will be equal to material D and will be equal to material E. But area of B will be less, area of C will be comparatively more than area of B. And that's why if we want the total area A, area is divided, heat transfer is also divided at this point. So total area will be equal to area of material B and area occupied by material C. And remember, the heat transfer rate will be same at every section, but only at this point, only at this junction, heat transfer will be divided. So let us consider that this is the temperature profile. The temperature is T1 at this point, this is temperature T2, and this is temperature T3, this is temperature T4, and finally let us say this is temperature T5 at the end. Remember, this entire surface will be at the same temperature T2, this entire surface will be at the temperature T3. Similarly, this entire surface will be at the temperature T1 even if we are showing it at a single point, but it is the temperature of this entire surface, and because of this heat is getting transferred from left hand side towards the right hand side. So let us connect the dots. Even though they are at same level, still there will be difference in this temperatures. I have just shown it to indicate that the entire surface is at the same temperature, like this. Also, let us say Ka is conductivity of material A, Kb is conductivity of material B, then Kc conductivity of material C, Kd, and finally Ke. Now we also need to have their dimension in terms of thickness. Area we have already discussed. Now we will discuss the thickness. Firstly, thickness of material A. Then remember, thickness of material B will be equal to thickness of material C. Then thickness of material D. And finally thickness of material E. So now we have set our stage. If you want, for the sake of practice, you can also include convection on this side and convection on this side and start drawing the network. Now we will draw the thermal resistance network, then we will convert it into mathematics. So now the first point, the junction will start at T1. It is not necessary that you draw the junction exactly below the wall. It is only necessary that you should incorporate everything which is coming in the path. You should not leave anything behind. So because this will be somewhat larger circuit, I am beginning from here, but anyways actually I am beginning from T1 only. So this is my first junction T1. This is the conduction resistance that I am going to represent. So this is my first conduction resistance up to T2. This is the T2. But at T2 I observe that heat will be divided into material B and material C. So this becomes a parallel arrangement. Firstly, heat is not divided in this part or in this part, but at this point heat will be divided. So this will be a parallel configuration, and that's why it will have resistances like this. So it will have resistance arrangement for upper material. So this will be conduction, that's why resistance of wall made up of material B, and the resistance at the bottom, this one, will be resistance of wall for material C. Then they will get connected and finally up to T3. Up to T3. We have come at T3 now. Between T3 and T4 there is a single material slab. That's why, and it is conduction resistance. That's why this will be resistance of wall for material D, and it is between T3 and T4. Between T4 and T5, same way, single material. That's why simple resistance of wall for material E, and this will be between T4 and T5. Now we observe that all the resistances have been taken care in this. Because of this architecture, heat will flow through the system, but heat will be divided at this point. At this point, heat will be divided, and the amount of heat flowing through this will be QC, amount of heat flowing through this will be QB. But then finally, total amount will be Q only by energy balance. Total Q will be flowing through the entire circuit. Now, the question comes, these three resistances, the resistance, my mistake, the resistance of wall for material A. These three resistances, they are in series with each other. Heat is not shared, area is not divided. But then what to do with these two? For such an arrangement, we have already calculated the equivalent thermal resistance. So now we will move on to the mathematics of it. So what do we get? This particular, simply we can express total heat transfer rate as delta T divided by summation of total thermal resistance. Now only the question comes, what is delta T and what is the total thermal resistance in the path? Whatever the delta T that we choose for that particular junction, and up to that point we have to write the equivalent, the total thermal resistance. So now we are considering total delta T, so we can write simply T1 minus T5 divided by this one, resistance of wall due to A, plus here we have to write down the equivalent thermal resistance. Why? Because these two are in parallel with each other. We have to convert it into equivalent thermal resistance. Then there will be wall C thermal resistance by conduction. My mistake, this will be because of material D, and then finally conduction resistance because of material E. Now, how to determine this R equivalent? The equation is simple now. As we know, this R equivalent is given like this. R equivalent is equal to 1 upon which two resistances are participating as parallel resistances? Resistance of wall for material C, resistance of wall for material B. So 1 upon R wall B plus 1 upon R wall C. So let us simply solve it. So it gives us, when we want to equalize the denominator, what we get? RWB multiplied by RWC, and we will take it, we will multiply the numerator. So what do we get? We get RWC plus RWB. Then, but this is the value of 1 upon R equivalent. We are interested in R equivalent. So it gives us R equivalent is equal to inverse of this. It is equal to resistance of wall of material B and resistance of wall of material C divided by resistance of wall material B plus resistance of wall material C, simply inverse of this entire quantity. So this will be formulation for equivalent thermal resistance. Remember, we started from a very simple step. Just 1 upon R equivalent is equal to 1 upon first thermal resistance plus 1 upon second thermal resistance, which are in parallel with each other. So now we have this R equivalent. Afterwards we can substitute it over here, and all the other resistances, if they are available with us, then we can simply put it in the equation and obtain the heat transfer rate. So all these are conduction in nature. So what we can write for them? If we want thermal resistance for wall of material A, it is simply, because it is wall, that's why it will be L upon Ka for material A. R wall for material B will be equal to L upon Ka, but all the quantities for material B. Remember, L for material A is different, L for material B is different. You have to substitute that individual quantity into this equation so that you can get individual values for these thermal resistances. And then once we have done this exercise, the nature of this circuit automatically changes, because now we observe that R equivalent is in series with all of them. So the circuit looks something like this. We will draw the modified circuit. After this calculation, after calculation of R equivalent, we get circuit like this. It will start from T1. There will be first thermal resistance, and this will be R vol A, and it will be up to T2. Then there will be, instead of these two resistances, because of mathematical calculation, there will be R equivalent up to T3. Between T3 and T4, there will be the next thermal resistance because of conduction, R vol for material D. Both of these resistances have been converted into equivalent thermal resistance. And finally, between T4 and T5, there will be the final thermal resistance R vol E. So in this way, simply by following a step-by-step approach, we have converted such a complicated system into this simplistic system. And whatever, now this is a simple series circuit. We have converted the combination of series and parallel into simple series circuit, because of which whatever be the junction that we choose now, we can simply put down the resistance, put the potential difference, and finally evaluate the heat transfer rate. So that's the beauty of electrical analogy, about which we are talking again and again, that it helps us to reduce such a complicated system into such a simple system of equations, so that our answers can become reliable as well as they come at a faster rate. Thank you very much.